Hello, my name is Fangshuo Liao. Today I will be sharing our work LoFT, finding lottery tickets through filter-wise training. This work is done with my colleagues Jihan Wang, Chen Dun, Chris Germain, and my advisor Anastasios Creditas. So I will first talk about some limitations in finding winning tickets for large CNNs, which would be the focus of our work. To start, the lottery ticket hypothesis claims that there exist good submodels of neural networks that achieve comparable performance to their whole counterparts. These good submodels are often called the winning tickets. The way to identify such winning tickets requires users to first pre-train the whole model until convergence, prune the weights that has a smaller magnitudes, and then after that, rewind the weights of the network to the initialization step and retrain this whole submodel. You can see that for a large neural networks, in order to find the winning tickets, this pre-training phase could be a burdensome task because the pre-training is done on the whole model. So our goal is to find an efficient distributed pre-training algorithm to find the winning tickets. Before we talk about our algorithm, let's first talk about some intuitions that we find from the observation of how the winning tickets emerges during the pre-training phase. We first propose a new filter distance metric F filter. To explain this F filter, let us first define the sigma, which is the permutation that maps indices of one filter ranking to another filter ranking. For example, suppose that one specific filter ranked number I in the first filter ranking, then it is ranked sigma I in the second filter ranking. And our function F filter basically measures how the first ranking differs from the second filter ranking. And our filter distance F filter is defined as the weighted sum of the absolute value of the difference between the two logs before and after the permutation. We choose the weight to be 1 over I because we want to put a higher emphasis on the filters that rank higher in the filter ranking. We will use this filter distance metric F filter to measure the distance between each pair of the iterations of training, basically the i's and j's iteration of training, and see how the rankings of the filters differs between the i's and j's iteration of training. The result is plotted on the right. In figure 1a, we have the pairwise distance for each pair of epochs for the layer conv layer 2. And in figure 1b, we have the same result for the conv layer 4. In both figures, we could observe that in the first 20-ish iterations, the rankings between the filters denoted by our filter distance metric is quite big, which is denoted by a lighter color. But in the later phase of the training, basically after 20th epochs, the filter distance becomes smaller. This means that the filter basically converges in the first 20 epoch and hardly changes in terms of the ranking in later phase of the training. So we could conclude that the filter, because the filter distance doesn't change, it means that the winning ticket emerges before training loss converges. So this means that we could possibly sacrifice some loss convergence for a better efficiency. So the idea is just to have an approximate way of training the exact neural network, which may result in a higher efficiency and also preserves the winning ticket. Our question is that, can we iteratively sample and train tickets from the large model? Why is this method helpful? Well, it is first an approximate way of training the whole model. And then, because we iteratively sample the tickets from the large model, these tickets can be trained independently on different machines, which is resulting in a distributed training algorithm. And more importantly, these submodels are smaller than the whole model. This brings us to our algorithm LoFT, the model parallel pre-training with filter partitioning. Algorithm 1 describes the high-level idea of the LoFT algorithm. We first randomly initialize a CNN. For each of the global iterations, we first partition the whole CNN into submodels. We distribute the submodels to the workers and let each worker trains the submodel for a number of local iterations using local SGD. After that, we will aggregate these submodels from the workers, and we will use the aggregated whole model in the next iteration and partition that into submodels and let the procedure continue. The partition method is described in more detail on the figure on the right. Basically, we will adopt a filter-wise partitioning strategy. In each layer of the convolutional neural network, we will partition the filters, meaning that for each worker, for each submodel, it will only take a part of the filters from the whole model. This will result in a smaller number of channels in the output, which also means that it will be a smaller number of channels in the input to the next layers. So in this way, we will shrink the number of parameters in each submodel. Next, we will provide some theoretical results on a simplified scenario of our algorithm. Let F be our one hidden layer CNN with W being its weights. We consider training on the dataset xi, yi's with n data samples, where each xi has a length of d. So the task we consider here is a regression task where the training loss is defined as the MSE. We will let Wt to be the weight trajectory of LoFT, and Wt hat be the weight trajectory of gradient descent. Let M denote the number of channels in the hidden layer, and S denote the number of workers. C denotes the probability of selecting a specific filter for a specific worker. We will consider the one local step LoFT, which means that each worker only trains LoFT for one local iteration. If M is lower bounded by n to the fourth times t squared times the max of n and d, where t is the total number of training iterations, then with a small enough step size eta, we will have that the expected value of the difference between the two trajectories plus the aggregated difference between the function output times the step size is upper bounded by some value here on the right-hand side of this inequality. The first term on the right-hand side scales inversely with the width m, which means that we have a larger number of hidden neurons. The first term will be smaller. And the second term here decreases as we have a larger number of workers, which means that if we have more subnetworks, this difference will be upper bounded by a smaller value, which results in a smaller error. Next, we will provide some experimental results of LoFT. We will first show that LoFT enjoys a lower communication cost. We tested our algorithm on the neural network architecture ResNet 34 on the Cypher 100 dataset and pre-ResNet 18 on the ImageNet dataset. The dense model achieves 75.93 accuracy and 70.71 accuracy, respectively. We compare our method with both the GPipe method, which is a popular model parallel training method, and local SGD, which is a popular data parallel training algorithm. We consider pruning ratio of 80%, 50%, and 30%. We'll compare the accuracy with two methods as well as the communication cost of these two algorithms. Our result shows that our LoFT algorithm when partitioned into 2 or 4 subnetworks, achieves comparable accuracy with the two baseline methods, while achieves improved communication cost. In particular, compared with GPipe 2 and GPipe 4, we will achieve communication cost improvements of 80 to 120 times. And compared with local SGD, we will achieve a 1.5 times communication cost improvement. The second result we have is that LoFT actually converges faster to winning filters. We compute and plot the filter distance between filters in each epoch and filter at the end of training using our filter distance defined at the beginning of the presentation. And the result is shown on the figure on the bottom, where the figure A shows the result on Cypher 10, figure B shows the result on Cypher 100, and figure C shows the result on ImageNet. We find out that filters trained with LoFT converges faster to final filters than baseline. Especially, we can observe that from the ImageNet experiments, where basically LoFT converges to the final filter in about 10 epochs, but our baseline converges to the winning ticket in like 20 epochs. In previous experiments, we measured the performance of finding the ticket with the filter distance metric between a specific ticket and the final winning ticket. In the next experiment, we will measure the performance of finding the ticket using the actual test accuracy of the ticket. We will sample the ticket in each stage of the pre-training with every 5 epochs step size. We will perform the fine-tuning on these tickets, which are submodels we obtain after pruning, and we report the final accuracy. The result is shown on the right. We will consider 2% of pruning, the 50% and 80%. We will compare our LoFT algorithm with the baseline GPEP algorithm, and we will also compare with no pruning. We observe that for all of the epochs and all of the pruning ratios, LoFT will achieve a ticket that has better test accuracy than the baseline algorithm. And after 15th epoch, for both the 50% pruning percentage and 80% pruning ratio, LoFT achieves a better accuracy than the model with no pruning. This means that LoFT provide better tickets consistently throughout training. As a conclusion, we first proposed a filter distance metric, which after experiments shows that winning tickets emerges before loss convergence. This implies that we can sacrifice loss convergence for efficiency while preserving the winning tickets. This gives intuition to our LoFT algorithm, which we proposed as a model parallel pre-training algorithm with the filterwise partitioning. We provided experiment results to show that compared with baseline, LoFT achieves better communication efficiency and also provides better tickets in terms of the convergence speed to the final tickets. We also provided the theoretical results to show that the LoFT trajectory stays near gradient descent trajectory, meaning that LoFT will not deviate too much from the traditional training scheme of gradient descent. And that's it for our work. Thank you.